Welcome to the ENOTEC webinar for the OXITEC in situ O2 analyzer. I aim to explain the importance of using a robust and accurate measuring technology in a combustion process. If you may have any questions or inquiries after watching this webinar, don't hesitate to contact ENOTEC. In previous webinars, I have introduced ENOTEC. For new viewers, ENOTEC is a mid-sized company based in Western Germany. ENOTEC produces analyzers for process control and safety monitoring in combustion and other industrial processes. For more information, take a look at our website at enotec.com. Let's start with the composition of dry air. The oxygen concentration is approximately 20.95%. The main component is nitrogen, around 78%. We then have some argon, carbon dioxide, and other trace elements. So the conditions for a combustion are as follows. Fuel is required, air, or more accurately O2 is required, fuel and O2 must be well mixed, and the ignition temperature of the fuel must be reached. The element of time is also required, of course. What is lambda? Lambda is the ratio of air to fuel in a combustion process. Lambda equals 1 is the stoichiometric ratio between fuel and air. This means that every single fuel molecule reacts with the oxygen in the air so that no unburnt fuel components remain and no oxygen is left. Lambda smaller than 1 means a deficiency of air, so combustion takes place with less air than would be needed in a stoichiometric reaction. Unburnt fuel is left. Lambda greater than 1 means an excess of air. A lot of oxygen is left in the flue gas. Unnecessary heat loss is the result, and this is wasteful and costly. In reality, lambda 1 is not possible because air and fuel are not homogeneously mixed. At the point lambda 1, unburnt fuel will be present in the flue. For more efficient combustion of fuel, a small amount of excess air is required after combustion. This graphic shows a theoretical combustion. In reality, the optimal lambda value differs depending on the fuel composition. Here in the graphic, the COE curves for coal, oil, and gas are shown, whereby gas shows the highest efficiency. Because of this, the measurement of COE in addition to O2 is more efficient for a combustion optimization. To increase the efficiency of a combustion, it's therefore important to measure COE in addition to O2. I will deal with the COMTEC O2 COE analyzer separately to explain this in more detail. So what are the consequences of a combustion with a deficiency of O2? In a standard combustion, carbon and O2 react and produce heat and CO2. In a combustion process with a reducing atmosphere, which is the deficiency of O2, the following happens. Iron oxide builds up on metal surfaces in oxidizing atmospheres. So in a reducing atmosphere with high CO, O2 molecules from metal oxide reacts with CO in the process to form CO2. If sulfurous coal is burned under such reducing conditions, sulfur cannot oxidize to SO2 and reacts with iron to form iron sulfide. Iron sulfide is not stable and is removed quickly by abrasion, which speeds up the destruction of the plant infrastructure. So, oxygen deficiency after combustion results in mechanical destruction of the plant infrastructure, such as refractory linings, furnace walls, boiler tubes, and more. Looking at the picture, this is a cracked boiler tube after approximately 2 years in a waste incineration plant. The wall thickness of the combustion chamber side of the tube has been reduced by CO corrosion and abrasion until the tube cracked. The measuring principle should measure the true net O2 content in the original wet flue gas and not in a dry sample. In an extractive dry O2 measurement, The process moisture is usually removed in the cooler of a gas conditioning system. So in the dry sample measurement, the O2 concentration is always higher than in a wet in situ measurement. So it may seem that the excess O2 is higher than in fact present. Looking at the graphic, measuring 5% O2 dry with 20% moisture in the process, the wet in situ O2 measurement will show 4% O2. Let's have a look at how the oxygen sensor works. The oxygen sensor is based on the zirconium dioxide O2 sensor. The sensor illustration shown in the first picture consists of an O2 ion solid electrolyte with an electrode on each side. One side is exposed to the process gas, on the other side reference air is applied. Zirconium dioxide becomes conductive at temperatures above 300 degrees centigrade. The process of ion conductivity is shown in the second picture. O2 molecules take 4 electrons from the first electrode to become O2 ions. These pass through the sensor to the second electrode and give the electrons to the second electrode and become O2 molecules once more. The direction of O2 ion flow is always from the side with the higher O2 partial pressure to the side with the lower O2 partial pressure. This process generates a voltage which is described by the Nernst equation. This illustration shows the measuring principle of the O2 sensor. See the process gas entering through the holes of the sensor protection cap. Here the reference air is shown on the inside of the sensor. Due to the difference in the partial pressures between the reference air side of the sensor and the process gas side, an O2 ion flow occurs from the higher to the lower partial pressure. In the Nernst equation, the generated voltage is dependent on the temperature of the sensor, a factor K which consists of natural constants, and on the ratio of the O2 partial pressures of the reference air and process gas. C is the constant offset voltage. By using a constant operating temperature and a constant reference air, the generated sensor voltage directly relates to the O2 partial pressure in the process gas, hence the O2 concentration in the process gas. So we've shown that for an O2 measurement to be exact, the sensor has to be gas tight. If the sensor leaks between the reference air and the process gas side, the sensor will measure leak air. As the leak air consists of around 21% O2, the analyzer will show a higher O2 concentration than present in the process. The measured O2 concentration will then depend on the leak rate of the sensor. In this graph, the actual O2 excess is shown, and the dotted line shows the hypothetical measurement of a leaking sensor. The leaking sensor always measures more O2. The DCS, which is the distributed control system, the operator will falsely reduce combustion air to a prescribed value when in fact the actual excess O2 concentration is much lower. This leads then to too high COE concentrations in the duct because there is not enough O2 for complete fuel combustion. In many zirconium dioxide oxygen sensors worldwide, cement is used to glue the sensor into the holder and separate reference air and process gas. Cement will after time develop cracks, and reference air, which is usually ambient air or instrument air, will leak into the process measurement side of the sensor. As shown in the previous slide, a leaking sensor will force the DCS operator to decrease the combustion air, leading to increased unburnt fuel in the flue. Detecting a leaking sensor is difficult. When applying calibration gas to the sensor, the calibration gas displaces the leak air due to the higher flow rate of test air. The measured value will thus be seemingly correct, when in fact this is not the case. In addition to our standard O2 sensor, which is highly robust and has a long service life, ENOTEC produces an Mlt O2 sensor. MLT is an acronym for multi-layer technology and is recommended for protection against aggressive components in processes such as waste incinerators or sulfur plants. Also, thermal power plants using coal with high sulfur content would be an application for the Mlt O2 sensor. The Mlt sensor uses an additional porous insulator as a sacrificial layer to protect the sensor from aggressive components, giving the sensor a long service life despite the harsh process conditions. MLT and CSP are recommended for aggressive and reducing atmospheres. Here is an illustration showing CSP. CSP, or cell surface protection, limits the purging of electrons by keeping the sensor voltage at a constant level. This is achieved by passing electrons from the process gas side of the sensor back to the reference air side of the sensor, so that oxygen ion migration takes place and protects the sensor against further reduction. That the ENOTEC analyzers measure correctly over a long lifespan is not only my opinion. We have many certificates to illustrate this. Firstly, we have the SEAL 2 certificate with a 1 out of 1 selection, meaning only one analyzer is required to reach SEAL 2. Secondly, OXITEC 5000 is suitability tested according to EN 15267 and is Qual 1 certified. The Qual 1 certificate allows a maintenance interval of 6 months, longer than any Qual 1 tested analyzer. Other certificates include the ATEX certificates I have discussed, with the additional IECEX certificate and the MCerts certificate. Of course, ENOTEC is certified to the ISO 9001-2015 Quality Management System. So what does an installation look like? This is a system overview of a typical OXITEC system. Here we have the controller connected to the in situ probe by the signal cable and pneumatic tubing. Depending on the requirements at site or user preferences, the OXITEC analyzer system is highly versatile and has many options. For example, the system is also available in a gas ATEX version, typically used in petrochemical industry, or a dust ATEX version, certified for use in applications with potentially explosive dusts, such as for sludge drying or in coal mills. Other options include probe insertion lengths of close to 4 meters, use of probe materials such as high alloys for the most demanding and aggressive applications. Typically, all systems are delivered with a fully integrated pneumatic unit, including a flow meter, pressure reducers, and solenoid valves, all built into the system and UI integrated. So, what are the typical installation points for the OXITEC system? Here is an illustration of a coal-fired power plant. The first measuring point would be after the economizer, before the air preheater for combustion control. Increasingly for this measuring point, the Mlt O2 COE analyzer is being put to use, but more on that in the Comtech webinar. The measurement after preheater serves as a delta O2 measurement to measure the leak rate of the preheater. After the electrostatic precipitator, the O2 measurement serves to monitor potential leaks. Using the Comtech analyzer at this point is for safety monitoring and explosion protection. After denox, the O2 measurement is an indicator of the effectiveness of the SCR denitrification. The O2 value is required for normalization of the measured NOx value. At the stack, the OXITEC can be part of the SEMS emission measurement as an O2 reference value. Please contact ENOTEC for this and many other application notes explaining the requirements and measurement points for ENOTEC analyzers. And that's it. Thank you for your attention. Please don't hesitate to contact ENOTEC if you would like to receive more information.